Okay, in this lecture we are going to study a little bit about the differential equation, what is the meaning of differential equation, and what is the geometrical interpretation of the differential equation. Differential equations has a wide range of application in many of the fields. Some of the fields I'm going to mention you here. In the fields of engineering, you might have seen the Navier-Stokes equation. Navier-Stokes equation in fluid mechanics. Sometimes you have seen the Newton's second law. How about the Euler-Lagrangian equation? You might have seen this equation too. Lagrange's equation. Except that you might have seen in heat and mass transfer subject the Newton's law of cooling. Law of cooling. Except that you might have seen the convection equations. These are some of the applications in the field of engineering about the differential equation. How about in the field of physics? In the field of physics, you might have seen examples of like radioactive decay. You might have seen Schrodinger's equation in your 11th-12th standard textbook. Schrodinger's equation. You might have seen or might not have seen the Poisson equation, which is specifically used for molecular dynamics, which is not our concern right now. There are certain fields like biology. It can be used in biology. For example, in biological population dynamics. You know how the cells are getting divided, how they are becoming exponentially higher and higher with time. These things can be solved with the help of differential equation. There is an equation which might be important to us in study of differential equation, which is known as Lotka-Volterra equation. This is once again for the population dynamics. Except that we have applications of differential equation in the field of economics. In economics, you might have seen the equations like used for population dynamics or used for spreading of a rumor, spreading of a disease. If you want to find out how many people are affected with Ebola virus right now on the planet, then you can calculate with the help of differential equation. It is basically defined by Malthusian law, which is again a part of differential equation. So as you can see, differential equation has a wide range of application in engineering, physics, biology, and economics field. You might have seen differential equation in your school level or the college level, such as y prime is equal to cos x, where y prime is actually dy by dx is equal to cos x. In India, we sometimes say y prime as y dash, so it might be confusing when I say y dash as y prime, right? You might have seen equations like this, y prime is equal to cos x, or you might have seen equations like d square psi by dx square plus d square psi by dy square plus d square psi by dz square equal to 0. Two types of differential equations are there. The first equation, here y is a function of only single variable, which is x here in this case. When a function, which is here psi, is a function of more than one variable like x, y, and z, and the differential equation formed by it is known as the partial differential equation, while this equation is known as the ordinary differential equation. So this equation is ordinary, and this is partial differential equation. We are not going to study about partial differential equations in this lecture or in this session right now. We are going to focus only on the ordinary differential equation. So you can say that differential equations can be divided into two categories, ordinary and partial differential equations. Let's try to solve this problem. Y prime is equal to cos x. When I tell you to solve this problem, what you are going to do, you are going to integrate it with respect to y and x, like dy by dx is equal to cos x. What I am doing here is I am taking this dx on this side so that y remains on one side and the terms containing x goes on the different side, and I start integrating it on the both side. So it will turn out to be y equal to sin x plus some arbitrary constant c, right? Now what is actually the meaning of this differential equation? What I am getting after integrating it? I am getting the solution of this equation. What is meant by the solution? Let's try to plot this y equal to sin x. If I tell you that c is equal to 0 in this case, what you will do? You will plot y is equal to sin x, which will look something like this. Of course on the negative side too. If I tell you that c is equal to 1, then what you will do? You will plot y equal to sin x plus 1, and the curve might look like this. How about c equal to 2? It will go higher. Similarly, for the negative term c equal to minus 1, it might look a little like this, and for c equal to minus 2, it will look like this. So let's write it down first. C equal to minus 2, C equal to minus 1, C equal to 0, C equal to 1, and C equal to 2. So as you can see, for the different values of C, I am getting different solution. So this is my general solution. This plot with various variable with different values of c, I'm getting different values of y, different values of solution, right? So this equation is known as the differential equation, which I have solved with y equal to sin x plus c, and I'm getting different solutions, which is known as the general solution. But if I tell you that my c is compulsorily 1, if I define in the beginning that for this equation the value of constant is 1, then you will focus only on this curve, right? So this curve is known as the particular solution. This is general solution, but this is particular solution of this equation. So solutions are in two types: general solutions and particular solution. When you have defined value of constant, you can get particular solution with the help of general solution. Now, the most simplest method to solve any differential equation is to separate variable, which you have done here. You have what have you done here? You have taken y on the one side, by x on the other side, and integrated. I am separating the variables, variable y on one side and x on other side. Let's try to do example based on the separable variable method, or method of separation of variable, method of separation of variables, right? I have a good example here which looks like 1 plus x dx plus x into 1 plus y dy is equal to 0. If I want to solve this problem by method of separation of variable, I have to take out y terms on the one side and x terms on the other side, right? For that, I am dividing this whole equation with the help of x into y. So 1 plus x into y divided by xy dx plus x into 1 plus y dy divided by xy equal to 0, right? Y gets cancel, here x get cancel. I'm just going to take this y terms on the right side of this equation. So 1 plus x divided by x dx is equal to minus of 1 plus y divided by y dy. Now what? Just simply integrate it, and after integration you will get ln of x, that means log of x, plus x equal to minus log of y minus y plus some arbitrary constant c. X plus y equal to ln of x into y equal to c, which is a solution. This solution is once again the general solution. If you try to plot the curve, the graph of this equation, then you might get something such as this, and by putting a particular value like c equal to 1 or c equal to 2 or c equal to 0 or c equal to pi, anything, you can get a particular solution out of the equation. Now let us move towards geometrical interpretation of differential equation. What is actual meaning of differential equation, why they are used in many fields. Let's see. You might have seen figures in your 11th standard or in the school level like this. Here I have a magnet with north and south pole. Right? Here I have a magnet with north and south pole, and this line, basically this line indicates the magnetic field, the magnetic region. That means magnetic field are indicated by the magnetic lines, that like field lines, right? What is the actual significance of these field lines? With the help of these field lines or the magnetic field, you can say that near the region of North Pole, the intensity of magnetic power is higher as compared to the middle portion. Similarly, for the South Pole, you can say the same, right? There are certain fields like magnetic field, such as here, or you might have heard the velocity field thing in the fluid mechanics, or acceleration field, or electrical field. There are certain types of field like this. Each of this field, if I take, let's say I have a velocity field like this, and if I take a point, arbitrary point here, then I can find out what is the value of velocity at this point if this field is a velocity field. Similarly, for if this field is an acceleration field and I take a random point here, then I can figure out what is the value of acceleration in that field. What I'm trying to tell you is that with the help of different types of field, you can determine the actual value of the quantity, right? Differential equation does the same. We have the Dirac field in case of the differential equations. Let's say I have a Dirac field something like this, right? I have Dirac field something like this. Now if I want to draw a solution out of this Dirac field, then what I will do, I will draw a solution curve which is tangent to this Dirac field at each and every point on this plane. And this is my solution and what it will look like. It can be here too. So this blue line is my solution, while the red sketch pen lines are actually the Dirac field. What is the meaning of this thing? With the help of Dirac field, you can find out the solution of the curve or the solution of the differential equation. Why we are doing this? There are certain equations which are not easily integratable. They are quite difficult to integrate, or maybe we need to use computers to integrate this equation. In order to do this with human mind or without actually integrating it, we can find out what is the significance of this meaning of this differential equation. What can be physical meaning of this differential equation with the help of Dirac field. If you know how to draw the Dirac field, the real question is how to draw the Dirac field. Let's try to do it with a simple example which I have seen in many mathematics books and many online available tutorials. Let's see. I have a differential equation of y prime into y plus x equal to 0. I want to draw. Let's try to learn how to draw a Dirac field in order to know what will be the behavior of the solution will look like without actually integrating it. For teaching this, I am going to use the simplest example that is available in the many mathematical books, and I have seen many lectures based on these examples. So I'm going to repeat that example. Right here is my standard example: y prime into y plus x is equal to 0. I can write this equation in the standard form like this, and I am equating this equation with some arbitrary constant c. Of course, I can write this equation like y equal to minus 1 upon c into x, right? These equations look a little like y equal to m into x, where m is the slope of the line. That means this equation is a line, basically. Let's try to draw this line. Let me draw here. If I take c is equal to minus 1 in this equation, then I will get a line like this, definitely, which is passing through origin, and the slope is 1. Right? Now I'm taking C as -1 here in this case. Now I'm going to draw a line whose slope is -1. So of course this line will be perpendicular to this, like this. And all this point, each and every point, I'm going to get a line like this, right? Instead of drawing the whole lines, I'm going to draw just short lines like this, right? These lines are also known as isoclines. Right? Y equal to mx, this is y equal to x line, where c is equal to -1 in this case. How about c equal to 1 line? For c equal to 1 line, I will get equation y equal to -x. So my line will look like this. For c equal to 1, I am going to draw the lines which have the slope equal to 1. That means the lines will look like a little like this. So instead of drawing the full lines, I am going to draw once again the isoclines. How about this line? I can draw isocline like this. I just need perpendicular lines for each and every line that I am getting from this equation. How about this? What will be the value of slope in case here? C is equal to 1. What about the slope here? Now let's talk about the slope here. C equal to 0, and slope here of this isocline will be infinite, kind of infinite, you can say, right? Alright, so I have a direction field like this. Now I can draw a solution of equation of this differential equation, of course. As I told you earlier, that to draw, let me show you first. If you have direction field with this red lines, then you can draw a solution with blue line like this, by just making it possible that each of the points on this direction field touches the solution curve, right? So I have to make a solution curve which touches each of these direction field isoclines, right? So let us try to draw. And my solution will look a little like this. How about these lines? Remember, my solution curve should be tangent to each and every of these isoclines, right? How about here? I will once again get a circular form of curve, right? I hope you get the idea of what I'm doing here, right? So with the help of direction field, I've got an idea about my solution might. Alright, so what we have done here, we have drawn a direction field in the red color with this small isocline with difference value of C and putting it into this equation, and we got the direction field, right? Now once we have a direction field, we try to draw a solution by in such a manner that each of these isoclines become the tangent of the solution, right? And without actually integrating this equation, we figure out that our solution might look a little like circle. Let's try to prove it analytically. That means directly integrating this equation. Y prime into y plus x equal to 0. Y prime equal to minus x upon y. That means dy by dx is equal to minus x upon y. In other words, I'm taking y equal y here and dx here. That means y into dy equal to minus x dx, and let's just integrate it on both sides. What I'm getting here, y square by 2 equal to minus x square by 2 plus some arbitrary constant, let's say k, we cannot use c of course here. So x square plus y square equal to 2 equal to k. We cannot use c here because it is already defined here, so that you do not get confused, right? Let's take 2 here, x square plus y square, and define some new constant k1. What is this equation? This equation is actually the equation of circle. By putting different values of k here, you can get different solution. Let's say if I put k here, I might get solution here, k1 equal to 1 here, then I might get solution like hey, this in a circle. If I put k1 equal to 2, then I might get solution like this. So different values of k1 will get me different values of solutions, right? So this is how the direction field is drawn.